All right, we are set out to prove that for each natural number n, so that's what this says right here, this set right here is the set of natural numbers. That would be the set of natural numbers, denoted with a bold-faced n like this, and it is simply all the counting numbers, if you did not know. 1, 2, 3, 4, ... We need to prove that for each natural number, notice that there are infinitely many of those, that the sum from 3, or the sum of 3 plus 4 plus 5 plus ... n plus 2 is equal to n times n plus 5 divided by 2. Okay, that's a big task, so I better get started. Let's start with n equals 1. What that means is I am going to plug in n equals 1 here. In other words, I'm only going to sum one thing on this side, so that'll be 3. Then I am going to allow n to equal 1 on this side. So that'll be 1 times 1 plus 5, all divided by 2. That is the same thing as 6 divided by 2, and that's the same thing as 3. So it turns out, if n equals 1, then this object, the sum of it looks like the first integers not including 1 and 2, equals 3. And then on this side, it also equals 3. So n equals 1, check. All right, let's try n equals 2. I'm going to sum the first two integers. So this side will be 3 plus 4, 1, 2, right? So n equals 2. On this side, what I'm going to do is plug in n equals 2 into this formula and hope that it equals 7. So on this side, it equals 7. Plugging n equals 2 on this side, it equals 7. And on this side, it's going to be 2 times 2 plus 5, all divided by 2. Again, all I did was I replaced these n's with n equals 2. And let's see what that equals. That's going to be the same thing as... well, these 2's cancel, so that is, well, 7. Okay, nice. So 7 does equal 7. I plugged n in on this side of the equation, it equals 7. N equals 2 on this side of the equation equals 7. So far, so good on the first natural numbers. We got a long way to go, so let's do n equals 3. We're going to sum 3 numbers on this side. I have to sum 3 numbers, so that's going to be 3 plus 4 plus 5. That's the same thing as 12. And I'm hoping that's going to be the same thing when I plug n equals 3 into this formula. So that's going to be 3 times 3 plus 5, all divided by 2. That's 3 times 8 divided by 2. And that's going to be the same thing as 3 times 4. And that's the same thing as 12. Oh my gosh, you guys. So it turns out this is going to take forever. I thought I could do it, but there's no way we're going to sit here this whole video and go through all infinitely many natural numbers and make sure that this equality holds each time for each n. I wish there was some sort of slick way for us to check all natural numbers. And you know what? Maybe let's come up with something. I think that if we can show that if this equality holds, what I can do is simply name this. Let's name this whole thing. I don't know. It's a proposition, so let's maybe call it P sub n. So that statement is a proposition that depends on n. If we can show that if is the biggest word in mathematics, if P sub k works or is true, then so is P of k plus 1, then I think that would be really nice. Because, for instance, if I knew this, then I would know that if P of 1 is true, then I automatically know, first of all, I do know that. I do know P of 1 is true. This is me showing that this proposition holds for n equals 1. I show that those two things are the same. If I can show that if p of 1 is true, then so is p of 2, that'd be great. And it also would be nice, I actually know that p of 1 is true. Wait a second, I've proven that p of 1 is true. And if I knew that if p of 1 is true, then p of 2 is true, then I would also know that p of 2 is true. But wait a second, if I know that p of 2 is true, then so is p of 3. Okay? So, like I said, if I can show that given any natural number k, that if I can also show that if this statement is true, this is a statement, by the way, then also the following statement of simply adding 1 to k is also true, then what I would inevitably do is actually show that all statements p of k are true for any k value. Because look, let's assume that I know that p of 1 is true. So two things I know. If both p of 1 is true, and 2, if p of k, if I also know that if p of k is ever true, then so is the next one then what would I know? I want to pose this question. In other words, I should say this, is ever true for some random k in the naturals? That's really important. What would I know? Well, let's see. I know that p of 1 is true. Here's my answer. And I'll say this, because I know p of 1 is true because of this first statement. So what I'm saying right now is let's assume that I knew both of these. Let's assume I know both of those. Well, then I would know p of 1 is true. So in other words, I would know that p of 1 is true. But wait a second, this second thing says if p of any number is ever true, then so is the next one. Okay, so what that means is that would imply p of 2 is true. Because what I have done, since p of 1 is true, I know that this is accomplished. If p of k is ever true for some number, then I definitely know the next one is true. So that would be because of 2, because of this second statement right here. But wait a second. If p of 2 is true, then p of 3 also has to be true. And that would be because of, yet again, this second statement right here. If I know that this proposition is true for any natural number, then I know that it's also true for the next natural number. And since I've shown that it's true for the first natural number, I automatically know it's true for the next natural number. And since I know that it's true for the next natural number, I know that it's true for the one following that. And this would continue. In fact, it would never stop. In other words, if I know if we can show that 1 and 2, and what I'm trying to do is eliminate me checking this statement for every single natural number. If I can show that 1 is true and 2 is true, so I'll write that down. If 1 is true in other words, it's a little weird, but I'm saying that if it is true that p of 1 is true, and the second one is true, this statement right here, if I can show that this statement is also true, Then, because of this argument right here, what would happen is kind of like a domino effect. That is like the quintessential analogy here. I can knock the first domino down for sure. If I know I can knock the first domino down, and if I know, so that's what this says. If I know I can knock the first domino down, and if I know that if any domino falls, the next one will as well, then what does that mean? That means that all dominoes fall. In other words, what that means is P of n is true for each of these n's. This is what I call mathematical induction. Let's see it in action with this case specifically. So what I'm trying to say here, go back to our original goal. So we want to prove that for each n in the naturals, this statement in the yellow box is always true. I have two jobs. What I want to do is to accomplish both of these green circles. So let me kind of reorganize here. Prove that for each natural number n, we know that 3 plus 4 plus 5 plus ... plus n plus 2 is always equal to n times n plus 5, all divided by 2. So that's our goal. I think I wrote that down correctly, right? We have to do two things. I'll start my proof like this. I'll actually start like this. Let 3 plus 4 plus 5 plus ... plus n plus 2 equals n times n plus 5 over 2. Let me name this inside my proof. So that's a statement. Okay, so that's a statement P of n, all right? So that's what that says. When we see this P of n, what we see is this statement right here. It's an equality. It's a proposition. We hope that it's a true proposition for each natural number n. We need to show two things. The first thing we need to do is show that the first domino falls. Okay? And the second thing we need to show, in other words, we need to show that P of 1 is true, if you wish. We've already done this, by the way, but we want to do it again within the proof. The second thing we need to show is that if, sorry, I had a little bit of a malfunction, P of k is true for any k bigger than or equal to 1, and that's this one right here, then so is P of k plus 1. All right, so what we're doing is, what we need to show is we can knock down a domino. We know this is true for some value of n. And then if we also know if it's true for some value of n, or for any value of n, then it's also true for the next one. Since it's true for this one, that means it's actually true for all of them. It's a domino effect. So what we say right here is one of the dominoes will fall. What we say right here is if any domino falls, then the next one will too. And since we know one of the dominoes fall, and that if any domino falls, then the next one will too, that quickly implies that, well, that means all dominoes are about to fall. And that is the principle of mathematical induction. So we need to show two things. First of all, P of 1 is true. This is what I call the base case. Or the base step, if you will. What we want to do is show that P of 1 is true. Well, like I said, what's going on right here is, to kind of illustrate this sum, that would be n plus 1. This right here would be, I'm sorry, n equals 1 plus 2. That's not what I meant to write. What this would be 1 plus 2. What this would be is 2 plus 2. And this guy right here is 3 plus 2. And that adds up all the way to n plus 2, of course. So what we're doing is we're summing on k. K ranges, or I'll say this, n ranges from 1, 2, 3, 4, to n. All right, so we want to check this first case, but we're only summing one thing in this first case. So we're wondering if 3, we only add one thing on this side, and that's just 3, is equal to this other side, except when we replace n with 1. So it's kind of like this. Best way to do this, let's see. Yeah. This is like n equals 1, n equals 2, and this would be adding those 3, n equals 3, and so on. So we want to check the n equals 1 case. We're replacing n with 1. We want to replace this n with 1. That's what we need to do. We need to show that P of 1 is true. So P of 1, to make it clear, I'll write this. P of 1 that statements, so I'm using a semicolon. I don't want to use the equal sign. Statements don't equal anything. Well, we would just have to create a literature with what equal signs mean for statements or propositions. P of 1 would be 3 is hopefully equal to, well, my favorite way to say 3 personally would be, I don't know, maybe 6 divided by 2. My favorite way to say 6 would be 1 times 6 divided by 2. My favorite way to say 6 yet again would be 1 times 1 in yellow plus 5 divided by 2. Oh, sick. So that is this side of the P sub n, this one right here, except with n equals 1. So I'll write this, n equals 1. And that would be the right-hand side right there. Notice all I'm doing is replacing n with 1 in that equation. And on this side, all I've done is added the first term right here, n equals 1 right there. So I showed that P of 1 is true. Now we need to show that if P of k is true for any k bigger than or equal to 1, then so is P of k plus 1. And here's how I do that. Let's suppose, this is called the inductive step. I'll back up. I'll call it the inductive step. Suppose P of k is true for some arbitrary k bigger than or equal to 1. There's nothing special about this. Maybe some isn't the best. Maybe any. I think some is okay. In other words, what would that mean? What would P of k being true mean? Let's suppose, so what P of k literally says is me simply replacing n with k in this statement. This yellow box is P of n, so I'm assuming that P of k is true for some k bigger than or equal to 1. So I'm supposing that 3 plus 4 plus 5 plus all the way up to n plus 2 is, k plus 2 is in fact equal to k times k plus 5 over 2. I'm supposing this is true, and I want to show that it is also true. I'll write that down. We want to show, and this is all within the proof, P of k plus 1 is also true under this assumption. So we are assuming this yellow box. We are supposing that this is true. We want to show that P of k plus 1 is also true. In other words, we want to prove that this statement, except instead of k, we have k plus 1. Instead of k, we have k plus 1 in all of these statements, is also true. So how are we going to do that? Like this. Notice that 3 plus, and I should write this, is true for some k bigger than or equal to 1. Notice that 3 plus 4 plus 5 plus dot 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 plus k plus 1, k plus 1 plus 2. Well, I'm hoping, I'll write this down. I think this is really important. All right, in other words, we want to show this is simply P of k plus 1 is equal to, so I'm replacing all of these k's with k plus 1. So that's going to be, that will look like this, k plus 1 times k plus 1 plus 5, all divided by 2. I also replaced this k with k plus 1. So we want to show, I am not assuming that this is true, I am hoping that this is true. All right, this is really important. But I am assuming that this is true. So I'm pretending for the time being that this is a true statement. I'm saying suppose that this were true. And I want to say that if this is true, then this has to also be true. This is called the inductive step. So in order to show this is true, what I'm going to do is start on one side of the equal sign here, and then just mold it mathematically, hopefully using this yellow box. By the way, this yellow box is called the inductive hypothesis. All right. Called the inductive hypothesis. I'm assuming the inductive hypothesis, and I am going to use that to show, hopefully, that this is true. So how am I going to do that? Well, I'm just going to start with the left side of this equation and kind of mold it mathematically. 3 plus 4 plus 5 plus dot, dot, dot. And I'm going to add in one term before this thing. So that's going to be k plus 2. The one right before this would be the kth term. And then I still have this k plus 1 plus 2. And I'm going to hope that this is equal to this. I'm not going to assume that it's equal to this. I'm hoping that this is equal to this. But I'm immediately noticing something. This thing right here is this thing right here. And the thing in this yellow box is something I'm assuming to be true. So if I assume that this object is actually the same as this object, I'm assuming that is true, I'm giving that as an assumption, then what I can do is simply replace this with this side. So that would be k times k plus 5 divided by 2 plus this extra term right here. K plus 1 plus 2, but I'm just going to write k plus 3. And I want to see something like this because of the inductive hypothesis. If you ever use the inductive hypothesis, you want to tell me that you just used the inductive hypothesis. So what I just did is I used this yellow box. And again, what I'm hoping to be true is for this to equal this. So let's hope for it. And of course, this is the same thing as k plus 1 times k plus 6. So let's see. This is going to be the same thing, of course, finding common denominators. That's k times k plus 5, all divided by 2, plus 2 times k plus 3, all divided by 2. Okay, but that's the same thing as, I don't know, let's see. We have k squared plus 5k plus 2k plus 6, all divided by 2. Okay, what is that? That's the same thing as k squared plus 7k plus 6, all divided by 2. Oh my gosh, you guys. Through factoring, look at how crazy this is. That would be k plus 1 times k plus 6, all divided by 2. And of course, that is the same thing. That should be a 5. As our k plus 1, k plus 1, and to make things clear, this is kind of like the initial k plus 1. And look, we did it. So what I would say next is, therefore, we use the inductive hypothesis right here and showed that the next domino had to fall. So overall, what we did is we showed, I don't even know if that's a word, that if P sub k is true, I didn't declare it to be true. I said that if it is true, then the next one has to also be true. And this has to be true for no matter what k is, as long as it's bigger than or equal to 1. But here's the thing. We already showed that it was true for the first case, which means combined with this inductive step, it has to be true for the next case and for the next case. And so we would end like this, end our proof. Therefore, by mathematical induction, this part's really important. 3 plus 4 plus 5 plus ... plus n plus 2 is equal to n times n plus 5, all divided by 2, for each natural number n. Okay, and that finishes your proof. This symbol, by the way, when you finish your proofs, it should be unique to you. This symbol literally means that that's what I wanted to show. It's kind of like your mathematical trademark. You could copy me if you want, but you should develop your own short symbol to finish your proofs with. I should be able to recognize who you are based on how you finish your proofs. All right, so let's see. That would be our first example of an official proof by mathematical induction. That was really important. Hopefully I've illustrated or convinced you why this works, but let's try it. Sorry, guys, I keep accidentally turning my iPad off as I move it around. Okay, let's try it again with this proof. Okay, so it's similar. We have a big old sum on this side. Let's do this a little bit faster. For our base case, the method for mathematical induction is you want to show that two things are true. That is this first case right here. Where'd it go? These two circles. We need to show that P of 1 is true, and that if P of k is ever true for any k in the naturals, then so is the next one. I should write any here. Those are the two goals that we really need in all of these proofs. So the first thing I'm going to write is the base case. And as sort of a thought bubble, show that P of 1 is true. All right, so on this side, I'm only adding one thing for p of 1. And then when I replace n with 1 on this side, hopefully these two things add up. So let's see. P of 1 is going to be the statement 1 over 1 times 2. Not 1.2, but 1 times 2. That is the same thing as 1 divided by 1 plus 2, and 1 plus 1, and I'm trying to emphasize that all I'm doing is replacing this n with 1. Just like how I replaced this n right here, we want to show that p of n, so I haven't done this yet, but this whole statement is our p of n. That is p of n. So all I'm doing is replacing n with 1 here. All of these n's with 1, and I'm hoping that it's true. This n right here is counting how many times you've added something up. So if I've only added one thing up, that means I only got this far. All right. Okay. Oh, hey, that is true. So we're already done. You can say P of 1 holds. The base case is done. We know this is true for at least one domino. We know at least one domino will fall. For the second thing, for this second part, what we're going to do is suppose P of K is true. For any k bigger than or equal to 1. In other words, suppose that indeed we have that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus ... 1 over n times n plus 1 is indeed, k over 1 over k times k plus 1 is equal to k divided by k plus 1 for k bigger than or equal to 1. I'm torn between any and some here. I think some is okay. For some k bigger than or equal to 1. If it is true for some number bigger than or equal to 1, then it's also true for the next one. Yeah, some works great. Some is a good word. I should change the other one to some, but that either way out, it's all good. We need to show that 1 over 1 times, or I'll say this, P of k plus 1 is also true. In other words, 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus ... Again, all I'm doing is replacing all these k's with k plus 1. 1 over, and I'll make that super clear by doing this, k plus 1 times k plus 1 plus 1 is equal to, hopefully, k plus 1 divided by k plus 1 plus 1. So again, all I did was I replaced this k with the purple one, with the purple k plus 1. This is what we want to show is also true. What I have right here, though, is what I call the inductive hypothesis. We're assuming that that is true. We're supposing that that is true. Can we show that if this is true, then this is also true? I don't know. Let's find out. Notice that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus ... What I'm going to do, I did this last time, is this is a sum that goes on as k ranges from 1 to k plus 1. So I'm going to include the term that came right before this, which will be the term that's 1 less than k plus 1. So this will be plus 1 over k times k plus 1 plus this term right here. Again, I scooted back a single term. And I'm going to drop the purple for now. So I'm going to notice that this is actually equal to, look at the nice thing, showed up again, that object we are assuming is equal to this. So this object right here is equal to this by assumption. It's called the inductive hypothesis. So I'm going to replace it. And again, hopefully when I whittle this away, we're going to land at k plus 1 over k plus 2. That's what we're hoping for. Let's find out. So we're assuming that this thing in yellow is equal to k over k plus 1. Again, that's because of this assumption right here. That's called the inductive hypothesis. And then I still have my plus 1 over k plus 1 times k plus 2. All right, and I'm going to say because of the inductive hypothesis. Common denominators. This is the same thing as k times k plus 2, all divided by k plus 1 times k plus 2, plus 1 divided by k plus 1 times k plus 2. And again, at the end, I am really hoping that this is equal to k plus 1 over k plus 2. So this is going to be equal to k times k plus 2 plus 1, all divided by, all divided by k plus 1 times k plus 2. And let's see. Oh, wow. Look at how beautiful this is, you guys. This is equal to k squared plus 2k plus 1, all divided by k plus 1 times k plus 2. This always blows my mind. And that's the same thing as k plus 1 squared through factoring, all divided by k plus 1 times k plus 2. One of these guys cancels. And what we have is indeed that is equal to purple, k plus 1 divided by, my favorite way to say k plus 2 is k plus 1 plus 1. And notice this. This object, our goal was to show, let me scoot back. Our goal was to show this right here. We started on this side using this side right here. Using the inductive hypothesis right here, we were able to go from this side to this side through all of these steps and land at the other side. And therefore, we're almost done. We know that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus ... plus 1 over, notice the change in letters here, really crucial. N times n plus 1 is indeed always equal to n over n plus 1 for each natural number n. And we've done it. I think I have one more practice question for you guys. Let's see how it goes. All right. Prove that for each natural number n, 3 divides this thing right here. Okay, so let's see what that says. What that means, by the way, 3 divides this object is 3 times some number is equal to this. 3 times some number is equal to this for no matter what n is. And I'll do a little bit more of an experience proof here where I won't tell you exactly what I'm doing. But within this proof is all the steps I need for a complete mathematical induction proof. So all I'm going to do is at the beginning, I'm going to say this. Notice there's two things, or recall, there's two things I need to do for a proof by mathematical induction. That's the base case and the inductive case, or the inductive step. The base step and the inductive step. So I'm just going to, without telling you that's what I'm doing, I'm going to do those things. Notice that 3, and I'll do this, times 0 is equal to 0, but my favorite way to say 0 is 1 minus 1 times 1 times 1 plus 1. So notice what I just did. I said that 3 times some number is equal to this object. Notice all this is me replacing this, or all the ends in this number right here, with 1. That's all this is. Notice that this is 0, by the way. So that's why another name for 0 is this object. But if 3 times some number is equal to this object, what that means is, therefore, 3 divides this number. Okay, so what I just did is I did the base case. I did the inductive step. I showed that P of 1 is true. So maybe I'll do this. That's what I just did. I don't need to write that in my proof, but the next step is I'm going to suppose that 3 divides k minus 1 times k plus 1 for some k bigger than or equal to 1. All right? Well, that would imply that 3 times maybe some number m is equal to k minus 1 times k plus 1. So I'll write for some m. And m would be an integer here. Then what I'm going to say, well, what I want to do is show that 3 also divides this object when I replace all the k's with k plus 1. So what I'm going to start with is this. So again, what I just did is, maybe I'll show with color. I replaced all these k's with k plus 1. What a mess. And I'm going to hope, assuming that this is true, again, this is what I call an inductive hypothesis. And really, this is also my inductive hypothesis. It's simply a rewording of this. So I'm assuming that this is true. I want to show that 3 also divides this object. All right, let's see what happens. This object is the same thing as, well, that's just k. This first guy's just k. And then I have, let's see what's next. K plus 1 times k plus 2. Okay, shoot. I really want this object to show up somehow. And let me think about how to do that. Well, here's the thing. I have a k plus 1, or a k times a k plus 1 here. I'm winging it, by the way, with you guys. What I really want is a k minus 1 to show up. I really wish this k plus 2 was a k minus 1, because like I said, this is a tool I can use. I know that this object, k minus 1 times k plus 1, is equal to 3 times m. But shoot, I really want to force this object to show up somehow. I already have the k and the k plus 1, but here I have a k plus 2. But guess what, guys? My favorite way to say k plus 2 is k minus 1 plus 3. Now, watch this. I can use the distributive property. I can bundle this up, distribute it to this k plus 1, then also distribute it to this 3. So this is going to equal k minus 1 times k plus 1 plus 3 times k plus 1. So again, all I just did was I grabbed this character right here, distributed it to the k minus 1, and distributed it to the 3. But look at how crazy this is. I am assuming that this object is equal to 3 times m for some integer m. In other words, this is equal to 3 times m plus 3 times k plus 1. Or excuse me, k times k plus 1. Oh my gosh, look at how beautiful this is. What I was hoping, this whole goal was, I really was hoping that this was divisible by 3. In other words, I really hope that 3 times some number is equal to this thing. So let's see. I think we're pretty much there. This is equal to 3 times m plus k plus 1. But guess what? That is simply 3 times, I'll go with L, or orange L. So check this out. What I just showed is 3 times some number. This is just some number, by the way. That's just, I don't know, an integer plus another integer. That's just an integer. And then what I just showed is 3 times this L is equal to this. And that's quite literally it, you guys. What that means is, therefore, 3 divides this object. And I'll do it like this. K plus 1 minus 1 times k plus 1 times k plus 1 plus 1. So what I just showed is that if this yellow box is true, then this is also true, and that is the principle of mathematical induction combined with the base case by mathematical induction. Three divides n minus 1 times n plus 1 for each n in the natural numbers. And that's it. Finish your proof.